This is section 3.7, optimization problems. Now this section is highly weighted towards application to real-world problems. One of the most prevalent problems we encounter for which we use calculus is for optimization. When we want to find the highest value of something or the lowest value of something, that's optimization. So, for example, if you ran a company, if you were looking at your profit equation, you would probably like for that to be at a maximum, I would assume. And again, if you're working for a company or own a company, I would think that your expenses, you'd want to have the lowest expenses you can. And all of that's solved using calculus in the realm of optimization. So let's do a problem. Let's say that we have a box and we have some restrictions on the size of the box that we can build. I'm thinking like a shipping company might have certain restrictions they would put on it or whatever, or the post office might have restrictions. But this box, so it's, I'm not very good at drawing rectangular prisms, but that's what it is. And let's read what they asked for us to have. I'm not sure I drew this, but that's okay. A manufacturer wants to design an open box, that is, no lid on this box, having a square base, so whatever this dimension is, let's say that the base is the bottom. This is going to be the exact same dimension. So if I call that dimension x, the other base dimension would also be x. So again, I don't think I drew a very good picture. And they don't tell us anything about that third one, so I'm going to call that the height of the box, or I could have used y. So I'm labeling all the dimensions of this box. Now let's read what they have to say about it. It has a square base, which we've indicated with our x, and a surface area of 108 square inches. Okay, so let's see. How would we calculate, and remember this doesn't have a lid, the surface area? Well, the surface area is going to be the base, and there's no top, so just the base, and the area of the base is length times width because it's a rectangle. X times x is x squared. Then each face, like this face here, will be x times h. So the area of that is xh. And how many faces of that size do I have? Well, since the base is square, although my picture doesn't show it very well, this face has the same size, as does the left face and the back face. So there are 4 of those that size. So that is a formula for the surface area of a box with no lid. And the question is, what are the dimensions of this box that will produce a box with maximum volume? So we need to maximize the volume. All right, so if we're going to maximize something, we need an equation for that thing. Like if you're going to maximize profit, you need a profit equation. If you're going to minimize expenses, you need an expenses equation. So since we're trying to maximize volume, we need an equation for volume. Well, since this is a rectangular prism, we know that the volume of it is length times width times height. That's x times h, or in other words, x squared h. And we want to maximize that. Now I'm going to tell you that the volume by itself is good. We want the v equals. On the other side, we don't want more than one variable. Okay? It's a little bit different from related rates in that we could have any number of variables and it didn't matter. But here we only want one independent variable. So we have to choose, do we want x or h? And how are we going to get rid of the other one? If we're going to keep x, how do we get rid of h? If we're going to keep h, how do we get rid of x squared? Well, the only way to do that is to have an equation that relates those two variables just to each other, involving numbers and operations. And in fact, we already have that in our surface area equation that we wrote down. That is an equation that relates those. So that's why that information of 108 square inches was given, so that we can write this equation, which we can use to get rid of either x or h. So, looking at this equation, would you rather solve it for x, notice there are x's in two places, or solve it for h? Notice there's only one h. Well, I'm hoping you're thinking solve for h, and that's what I'm going to do. So to solve for h, I'm going to subtract x squared from both sides to get this going, and then divide both sides by 4x. So anytime we're doing an optimization, that is getting the greatest, biggest, most of something, or least, smallest of something else, we can only really deal with one independent variable. So we'll have our dependent variable for volume, but we want this to be in terms of x or h. And by solving for h, we're replacing h with something, and it's in terms of x. So this will now be a function of x. Notice I wrote v of x, now that it's completely in terms of x. So I'm going to take the h out, and in its place substitute 108 minus x squared all over 4x. Okay. So what would we do next? Well, I would simplify as much as I can. Let's see. There's several ways I could do this. So I'm trying to make a decision. I'm going to split this into 108 over 4x minus x squared over 4x. And there are other things I could have done first. I could have distributed the x squared first, for example. And that's what I was contemplating as I hesitated there for a second. But anyway, we can do it. Do the distribution later. See, 4 goes in 108 27 times. So that's 27 over x. And a single x cancels, leaving x over 4. Okay, make sure that everything's right. Now I'll distribute the x squared. So that's going to leave 27x minus 1/4 x cubed. Notice I wrote that division by 4 as a coefficient of 1/4. Again, for derivative purposes, that's a better form. Speaking of derivatives, if I want to find a relative max or a relative min, which is, that local max or local min is the greatest value or the lowest value possible. So hopefully you're seeing that optimization is really just finding extrema. Okay. Now, so to do that, we're going to use the first derivative to find extrema. So the derivative of this is 27 times 1 minus 3/4 times x squared. Set that equal to 0, because we're finding critical numbers. Or make sure you consider where the first derivative ever fails to exist. For this polynomial, that never happens, so we just need to give it a nod that we've thought about it and go on. So down here to solve, since there's no x term, I think I'm going to isolate the quadratic term, and in fact go so far as to multiply both sides by 4/3. to get rid of the 3/4. And then take the square root of both sides, getting plus or minus 6. Now realistically, x is the dimension, the length of a side of a box, and it can't be negative, and I do get that, but I'm pretending like I'm just kind of blindly doing a number line analysis, including everything that doesn't actually have an effect here. And it doesn't hurt to do more than you need. Just don't use more than you need as a potential final answer. That would be kind of bad. Okay, so those are places where it's equal to 0, 6, and -6. I meant to mention this earlier, and I realized I forgot it. You know, what we've been doing is calculating for each chunk of that domain with a number. We substituted like -7 in to see what's going on to the left of -6. Maybe substitute 0 in to find out what's going on between -6 and 6, etc. The other way you can do it is if that graph is something that you can graph easily. That's a parabola that opens downward, whose x-intercepts are -6 and +6, which is what we got when we set it equal to 0. And -3/4 means that it's opening downward. If you can graph that correctly and look at it, this first part where the graph is below the x-axis, you're getting negative y values for that. That means that from -infinity to -6, you're going to get negative values. Then, between -6 and 6, all of these values are above the x-axis. They're positive y values. So that means that between -6 and 6, the answers will be positive. And then finally, to the right of 6, these answers are negative because they're below the x-axis, which means that everything to the right of 6 will have negative answers for v prime, because this is the graph of v prime. And what this plus and minus and all that stuff means is what kind of v prime answers are you getting, y values are you getting. And if you can graph that fairly easily, you can do this to find your positive and negative values in place of doing the substitutions if you want. If you still want to do substitutions to find that it's negative, positive, negative, be my guest. I'm not opposed to that. I just want you to make sure that you have alternatives sometimes. That's a good idea. So anyway, that means that the velocity function is decreasing, increasing, and decreasing. And of course, in reality, I don't know what the exact domain is, but certainly we can't have a length that's smaller than 0. So that's our domain, is bigger than 0. So taking that into consideration, 6 is the only possible thing for us to get an answer from. And of course, since the first derivative changes from positive to negative at 6, that means that that's a local max. And it's the only local max, and everything from 0 to 6, it's only getting bigger until you get to 6, and then after 6, it's only getting smaller. So that is actually also, on our domain, the absolute maximum value. Again, because we only had one candidate for a local max, and otherwise everything else for positive x's would have lower v values. So that is the absolute max when x is 6. Now the original question asked us to find the dimensions. So one of the dimensions is x is 6 what? Do you remember the units? Well, the surface area was given in square inches, so 6 must be measured in inches. And then what's h? Well, we should go back up to the top and look and see what h is equal to. And if you look at the very top there in pink on the right, That's what we're going to use to find h. 108 minus x squared divided by 4x. 108 minus x, which is 6 squared, or 8 minus x squared, I've already forgotten what it was, all over 4x, oops, divided by 4x, so 4 times 6, and h ends up being what does that end up being? Oh, that ends up being 3. Yeah. So the box is 6 inches. Of course, that's a mark for inches. By 6 inches by 3 inches. Those are the dimensions of that box that has the greatest volume it possibly can, with the restriction that the surface area of the box with no lid, the surface area has to be 108. Okay, so there we go. So applied minimum and maximum problems right after example 1 are some guidelines for solving applied minimum and maximum problems. First, identify all of the given quantities and everything that's to be determined. If possible, make a sketch. And at this point, you probably would want to label the things you're finding, like I labeled the dimensions of the base of that box as x, and the height I called h. And those are the things that I needed to find. And I stated that the surface area was 108. Write a primary equation for the quantity that is to be maximized or minimized. In this example, it was the volume equation, because that's what we needed to maximize. And it gives you a hint that there are a lot of useful formulas from geometry that are in the cover of your book. Maybe the back cover or front cover, I'm not exactly sure where it is in your book, but that's a nice little thing you might need to look at. Simple things are things that I would expect you to know. The more difficult ones, like surface area of a cone, I'm not going to expect you to know that one. So anyway, 3, reduce the primary equation to one having a single independent variable. Remember, ours had x and h. And we had to do that substitution with our secondary equation, the equation set equal to the 108 that we solved for h, that we substituted in to that primary equation to rewrite it in terms of a single variable. So again, that could involve the use of a secondary equation, and maybe more than one, that relates the independent variables to each other, x and h related to each other, so that we could get rid of one of those letters and have only, in our case, we decided to stay with x. We didn't actually find the feasible domain, as they suggest, but do think about, well, can I have negative numbers? Would it make sense for like x to be 1,000? Is that even feasible? And so in other words, your answer has to make sense. It has to be an actual real number that makes sense in your problem. Then desire the max or min value by using calculus techniques, like we use the number line analysis. Okay, let's do another problem. This one says, which point or points on the graph of y equals 4 minus x squared are closest to point or points. I'll write points in case there's more than one. The points closest to the point 0, 2. Sorry, that was my phone reminding me of something, so just a second. So to find the points closest to the point 0, 2 that this curve approaches, let's look at this graphically and see what we're dealing with. Of course, the parabola is one that opens downward with a y-intercept of 4 and x-intercepts of -2 and +2. And the point 0, 2 is right here. So we're going to find the coordinates of the points closest to that point. And I know that where I'm going to draw this point is probably not correct. I do not think this is the closest point that that curve has to the point 0, 2. But I'm just drawing it away from where I think it is to underscore the fact that I'm using a generic point xy. And for it to be close, think about what we're going to have to measure to determine closeness. What do you think that would be? Well, I was thinking it would be the distance between those 2 points. And if distance is something that we can quantify between those 2 points, the generic xy point and on the parabola and the given point 0, 2, what we're going to want to do with that distance to get the closest points is we're going to want to minimize. Well, I should have given myself more room. Minimize that distance. Okay, so we're going to have to come up with an equation for distance between 2 points. And the good news is we have one such equation. It is called the distance formula. So the distance between 2 points is x sub 2 minus x sub 1. I'm thinking of the point on the parabola as the second point, and the point we're given as the first point, squared, plus y sub 2, y, minus y sub 1, 2, squared. Now, that radical in there is sort of troubling to a certain extent because I don't want to have to deal with a radical if I don't need to. So what I'm thinking of doing here is valid, that if I'm going to get a minimum distance, what would the square of that distance, which I'm going to call capital D, have to be? Well, since the square root radical function is an increasing function, if I have the smallest radicand, the smallest thing that goes into that radical that I can get, then that's going to make the radical the smallest it can be. So like if the smallest is 9, the square root of 9 would be 3. But if I could get a smaller thing under the radical like 4, its distance would be square root of 4, 2, which of course is closer than 3 was. So I can do this, and what I'm going to minimize distance, how I'm going to minimize distance is I'm going to minimize the square of the distance. And it will give me the same answer, and it's a lot easier to deal with. Okay, so the distance, the square of the distance, capital D is what I'm calling that, unfortunately has two independent variables, x and y. We're only allowed one. So how is one to rewrite that in terms of either x or y only? And it really doesn't matter which one we choose, by the way, because we have to find both x and y eventually. Well, The equation, which is secondary here, is the equation of the parabola itself. That's the relationship between every xy ordered pair on that parabola. So we can either substitute for y, and that'll be in terms of x, or we can substitute for x squared, and that will then be in terms of y. It doesn't really matter to me which way we do it. You may feel like one way is easier than the other. I'm going to outline both of them so that you have a clue as to what the possibilities are. If I used the equation as is and substituted for the y with 4 minus x squared, replacing the y in the capital D equation, this is what I'm going to end up working with. And that ends up giving me an x to the fourth. Think about that for a second. I've got x squared inside of this big set of parentheses, and it's going to be squared. So there's going to be an x to the fourth in this problem, and that may make some of you a little bit anxious. So the other thing we could do is we could solve the given equation, what we're using as the secondary equation, for x squared by first subtracting 4 from both sides and then multiplying both sides by -1. And then substitute for x squared into the D equation, and that's going to be 4 minus y, replacing x squared. Notice I didn't need to solve for x, plus y minus 2, quantity squared. And you can minimize either of these forms, the D in terms of x or the D in terms of y. My perception is that the one that involves y is easier. So I'm going to use that one as an exercise if you want to try the other one. Might be fun. If you think of that kind of thing as fun, it would be fun. Okay, then doing the squaring, that's y squared minus 4y plus 4. And so distance in terms of y simplifies to be y squared minus 5y plus 8. Okay, so for optimization purposes, we always are going to go with the first derivative and the number line analysis. So that's 2y minus 5. Find out when that's equal to 0, or when d prime of y doesn't exist, because that's a polynomial, linear polynomial. That's never an issue. And over here, y is equal to 5/2. Okay, so if we do the number line analysis for d prime, that will tell us what's happening with d. 5/2 is our only critical number, and I got it from equal 0, so a nice solid dot there. Okay, looking at our derivative, if I pick a number to the left of 5/2 like 0, 2 times 0 minus 5 is negative, which means d is, oops, I wrote the wrong thing. I was about to say decreasing and writing increasing. Weird. Don't know where that came from. It's decreasing. And if I pick a number bigger than 5/2 like 10, 2 times 10, 20 minus 5 is positive, and so that means that d would be increasing. And so we have a relative minimum when y is 5/2, 5 halves, 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 5 And let's see, what's our domain for y? Because it's considered an independent variable here. What are the values of y? Well, the domain of y is negative infinity to 4. So if before 5 halves it's always decreasing, and then after 5 halves it's always increasing, that is, 5 halves is our only critical number in the domain, that relative minimum is actually also the absolute minimum. And that's what we're looking for, is minimizing d, and that occurs again when y is 5 halves. So we're going to let y be 5 halves as an answer. And now we need to find, well, what's x? Well, our equation to find x, we can use one of several, but I'm going to highlight one that has x almost by itself, this one right here. That means that 4 minus 5 halves would be x squared. Let's see, 4 minus 5 halves is 3 halves. That's x squared. And so that means that x is plus or minus the square root of 3 halves. Fractions under a radical are not considered simplified. So generally speaking, we split that into the square root of the numerator over the square root of the denominator, and then rationalize, and that will give you the square root of 6 over 2. Well, plus or minus that. All right, so our question was, what are the points on that graph that are closest to the point 0, 2? The points closest to 0, 2 are positive square root of 6 over 2 paired with 5 halves, and then negative square root of 6 over 2 comma 5 halves. And that probably shouldn't surprise you much, because our parabola is symmetric with respect to the y-axis, and so those points are points of symmetry. And let me see if I can just locate them for you. Of course, I don't have a perfect graph, so please be kind. See, if 5 halves, that's 2.5, so that point must be right here, and the other one is right here. Those are the locations of the 2 points where y is 5 halves, and x coordinates of those points are square root of 6 over 2 and negative square root of 6 over 2. All right, so that finishes that example. And I think that's the end of this section of notes, so I will see you in class.